Welcome to the final video in this series where we write an application in language DMQ. Throughout the series, we've written machine language in format DMP, which is like a hex dump with comments. It's tedious to compute byte counts and jump lengths in DMP programs. When I write a DMP program and first go to run it, usually it fails. I add or remove some bytes and I revise counts and lengths throughout the source file. This could happen many times. You might say this is why no one programs in machine language. In the last video, we invented language DMQ to address this problem, and we wrote a compiler. The compiler puts out a binary stream. Bytes of the stream have locations numbered from 0. Locations are the same as the byte counts we write into our DMP source files, but locations are part of the DMQ language, not just annotations in the comments. The compiler knows the current location in the output stream. When the compiler sees a number followed by white space in the DMQ input stream, it writes one binary byte to the current output location and adds 1 to the current location. DMQ also has comments, as in DMP, and DMQ has colon, plus, and minus. Colon sets the current location to a given location. Plus writes to the current location the 4-byte address corresponding to a given location, then adds 4 to the current location. Minus writes to the current location the 4-byte length of a jump from the current location to a given location, and adds 4 to the current location. With DMQ, we can refer to locations by brief numeric labels, we can move blocks of code around the executable by relabeling the source file, and we can get the machine to compute jump lengths for us. The language is simple enough that we can write a compiler in machine code. DMQ is not everything we want in a programming language, but we might want DMQ when we write from scratch a compiler or interpreter for a higher language. I've made changes to the DMQ compiler since the last video. Before we go on, let's take a look at the new version, 8DMQC. The program segment begins with a library. Left of the dash in these comments is a little note about the state of the machine before a call to this function. Right of the dash is a note about the state after this function returns. Function putout invokes Linux syscall write to put a string out to the standard output stream. Registers ECX and EDX contain the address and the length of the string. After putout returns, the flags are negative for error or 0 for OK. A caller of putout can use the flags to handle errors. A question mark indicates that the function might change the value of the register. Function takeIn invokes Linux syscall read to fetch a single character from standard input in the buffered way of video 5. After takeIn returns, the flags are negative for error, 0 for done, or positive for OK. In case of an error, the exit routines make it convenient to exit the process with a suitable status. That's the library. The compiler uses the library routines itself, and the compiler copies the library routines into each executable it produces. We were already copying the compiler's elf header into the output stream. It's easy enough to copy the library too. That's done here in copy header. The compiler and each executable it produces start running after the library at location 82. The corresponding address is in field E-entry of the elf header. EDI keeps the current location. EDI is set to 82 before DMQ input is processed. Function getByte saves our accumulator EBX by pushing it onto the stack. Sets EDX for library function takeIn, calls takeIn, exits with an error status if takeIn fails, pops EBX from the stack, jumps to routine finish if there's no more input, and moves the current input byte into register AL otherwise. Routine finish sets ECX and EDX for library function putout, calls putout to write the executable, exits with an error status if putout fails, and exits with normal status otherwise. Here's where the compiler processes input. Word is the state where we're ready for a new input word. We return to this state after each input character except for hash or numerals. The ELF program header contains the segment length in field P file size. In this version of the compiler, we update P file size throughout compilation by recording there the greatest value achieved by EDI. We clear our accumulator EBX and we're ready for a new input character from function getByte. What happens next depends on the input character. The compiler applies a sequence of comparisons and jumps to find the right routine to handle the character. This little key gives the order of the characters as defined in the ASCII standard. Character hash starts a comment. We skip bytes until the next new line. If the character is whitespace and the accumulator is non-empty, we write a byte from the accumulator. If the character is a numeral, we update the accumulator and go back for another input character. If the character is colon, we set the current location to the accumulator. If the character is plus, we convert the accumulator to an address and write the 4 bytes. If the character is minus, we compute the difference between the accumulator and the current location and write the 4 bytes. We make 8DMQC, and it compiles the sample DMQ program, 7T3, successfully. Let's write some applications in DMQ. Program 8A prints Hello World several times. There's no elf header in the source file. The compiler writes an elf header for us. The first bytes of the program begin at location 82. We pick a location 200, well beyond that, where the loop begins. Okay, I guess we're still counting bytes, just not precisely. Let's look at the binary. These 5 bytes at location 82 are the first instruction of the program. These 5 bytes at location 200 are the first instruction of the loop. In the binary, there's a gap caused by the 200 colon. You might expect that the gap is filled with harmless no-operation instructions, but it's not. If we let the machine run into the gap, our process may crash. To avoid a crash, we jump the gap. At the bottom of the loop, we jump back to the top. String hello world is encoded in ASCII at location 300. We refer to that location when an x86 instruction needs an address. Program 8B prints a number. The number in EAX. As in video 4, we repeatedly divide by the number base. The number base is at location B00, which we can access by a special addressing mode that takes a 32-bit offset only. The algorithm produces numerals from least to most significant, that is, right to left, but numerals are printed left to right, so we store them in a buffer before we call putout. Remainders range from 0 to 15, but the output stream needs ASCII characters. Back in the DMP days, we converted to ASCII by machine language arithmetic. But in DMQ, we're willing to spend a little space if it makes the programming easier. Here we construct a table and look up the ASCII values. This table is two-way. It converts hexadecimal numerals to and from ASCII. Program 8C prints a list of numbers. I've borrowed code from Program 8B, especially blocks space, numeral, and right. There's some new loop business above and below. and function show encloses all this. Show is called once. If ever putout fails, we exit with an error status. Otherwise, show returns and we exit with normal status. The list of numbers is given in an array down here at B04. Each number is 4 bytes long, but we don't have to provide all 4 bytes. DMQ lets us skip around the executable. Locations we don't write are 0 valued. According to the System 5 ABI, when p-mem size is larger than p file size in a loadable segment, the extra bytes are initially 0. So locations beyond p file size of program 8C are 0 valued, as Linux obeys the System 5 ABI on 0 initialization when program 8C is loaded. Locations from 8.2 to p file size of program 8C are also 0 valued, except of course for those locations written according to the DMQ source code of 8C. The compiler's output buffer is beyond location p file size of the compiler, and Linux zeroes the buffer when the compiler is loaded. Untouched by the compiler, these locations remain 0 valued when they're written to the compiler's output stream. There's a special addressing mode for scaled index and 32-bit offset, but no address base. Program 8D takes numbers from standard input and prints them. Lowercase hex numerals are accepted. At the top of the program, we set a couple registers, and then we start processing input. Numbers are gone from the source file as they come from standard input now. Like the compiler, this program takes input characters one at a time and acts according to the kind of character. There's a word block where we clear the accumulator. There's a char block where we fetch a byte. For each input character, we need to find the right code to handle it. In the compiler, we did this by a sequence of comparisons and jumps, but in program 8D, we look up the location in a table. Actually, 2 tables. Table char to act on the left maps ASCII characters to single-byte integers. These integers, let's call them signifiers. Table act to doer on the right maps signifiers to addresses. Suppose, for example, that the input character is a space. Space has ASCII value 20. 20 plus the address C00 of the left table equals C20. We look up the byte at C20. This is done in the machine by a move instruction. C20's signifier is 04. There's nothing special about the value 04 except that D04 is the next location available after D00. 04 plus the address D00 of the right table equals D04. We look up 4 bytes at D04. This is done in the machine by a jump instruction. D04's content is E20 plus. E20 is the location of the code that handles whitespace. There's nothing special about the value E20 except that it's a convenient place for this code. The table has entries for tab and new line, also handled at E20. Suppose for another example that the input character is a numeral 5. Numeral 5 has ASCII value 35. 35 plus the address C00 of the left table equals C35. We look up the byte at C35. There is no byte at C35 in the source code, so the signifier is 0 due to 0 initialization. 0 plus the address D00 of the right table equals D00. We look up 4 bytes at D00. D00's content is E00 plus. E00 is the location of the code that handles numerals. You might say that our program handles characters as numerals by default. The Postfix calculator of program 8E also has a list of numbers. We can append a number to the end of the list. We can drop a number from the end of the list. We can change the number base for input and output. To perform an arithmetic operation on the last two numbers of the list, we type the operation after the numbers. We can add two numbers, subtract two numbers, multiply two numbers, divide two numbers, discarding the remainder, or negate a number. I modified function show to print negative numbers nicely. And I added to the tables entries for calculator functions, plus, minus, and so on. To drop a number, we shrink the list by 1. For operations, plus, minus, and so on, it's convenient to have this function pop that moves the last number of the list into register EBX, shrinks the list by 1, and moves to ECX, the address of the new last number. Then addition is just pop followed by an instruction to add EBX into the number at ECX. Subtraction is similar. Multiplication and division are a bit different. There's an x86 instruction to negate. The change of base operations just move an immediate byte into memory. And that's it. We have a text-based calculator application for Linux in under 200 lines of DMQ source code for the application, and under 200 lines of DMP source code for the program that compiles it. No linker, no assembler, just x86 machine code. Thank you for watching this video. Please share it around.